Okay, thank you very much. I will also time myself just to be on the safe side. Thank you to the organizers for the kind invitation. So this is something that we have started as a project for the Diego Velosa Diaz PhD thesis. So this is relatively recent, and there is a manuscript that has been just submitted. So, okay, so we want to develop a model for the kinetic transfer of electrons in a single half cell, so in an electrochemical half cell. So then this is the outline of the talk. First, I will discuss the model. So first, I will need to introduce the motivation. Why are we dealing with this kind of situation, this kind of modeling? Why we believe is useful, could be useful. Then I will go into discussing the details of the model, so the different components that we need to take into account, grand canonical simulations, because we want the electrolyte to be in contact with an infinite reservoir of particles. And also we will discuss the surface hopping of electrons between the electrode and the cations, in this case, close to the interface. Then I will present some results, summary and discussion, and then I will have a bit of comment on an alternative method to perform grand canonical molecular dynamics or Monte Carlo simulations for fully atomistic systems. This is also something in which we have been working for quite some time. So this is the problem that you have seen already several times in this workshop. So then you have an electrode, you have an electrolyte, and then our aim here is to simulate the charge transfer that happens between the electrode and the cations close to the interface. So here in this, let's say, active layer. The idea is to take into account the granularity of a charge, which is not taken into account by mean field methods like density functional theory. And also the idea is to have a stationary steady state current circulating in the system. So we would like to impose that, and we would like to characterize this in this simple model and see what happens. So this is perhaps the simplest device that we can consider. This is a half cell model. So essentially, as we have seen also before, we have an electrode. The electrode has a Fermi energy. And then you also have the orbitals of the cation and the anion. They tend to align with respect to this Fermi energy. The situation that we will discuss here is actually when the lowest unoccupied orbital of the cation is below the Fermi energy of the electrode, meaning that there is a tendency for electrons to go to the cation, but not to the anion. So what are the challenges that we are facing in this problem? So first of all, we are trying to mix quantum and classical aspects. So here is the quantum mechanics there. Classical aspects, yes, of course, because we want to see what is the effect of the actual current of ionic current and diffusion of ions. So these two phenomena we would like to investigate on equal footing. This is very important. There is a different time scale for electron kinetics and diffusion of the ions. This you can see it comes from from Marcus theory. So then there is an energy barrier for the electron to jump into the ion, and this energy barrier could be easily larger than EVs. So then that means that we are dealing with some sort of rare event whose scale is more or less of the order of nanoseconds. On the other hand, we have the diffusion of the ions. If you have done some molecular dynamic simulations, you have probably computed velocity autocorrelation functions, and then you see that actual ions or molecules in your system became Brownian, so follow a Brownian motion after a few picoseconds. So then we are trying to reconcile picosecond, nanosecond timescales. On the other hand, we have the large size that we need for this electrolyte here. So, and this is very important because what happens is that eventually electrons will jump into the cation, and then these neutral particles will just disappear, or saying in a different way, what you will have is depletion of cations, okay, induced by the electron transfer. And then the ions here, they will try to go into the system. And we know from experience that these depletion effects close to an interface, they are highly dependent on finite size of the simulation box. So then ideally, we would like to either have a large simulation box or sample Grand Canonical ensemble. So what I'm trying to say here is that, and this is something that probably you know, is that the problem is a multi-scale problem, not only in size, but also in time. Okay, so this is our approach. So I will give a general idea, and then I will go into the details. So we focused first on the reduction of the cation close to the cathode. And then, as I said before, so electron jumps into the cation, and then the new cations will come to the interface, no? So they will diffuse. So there is an interplay between the two effects. So then here there is an schematics of the electrodes, the so-called active layer here, cations and anions in different colors. Why is it a curved surface for the electrode? Why I draw it in this way will become clear in a moment. So then essentially this is what is happening. So you identify these cations that are in this active layer, they get neutralized, and then they just diffuse like every other ions in the system. So the input parameter or state variables for our simulation would be a concentration of ions, the temperature of the system, and the dielectric constant. Dielectric constant because we would like to have an implicit solvent model. In this case, we consider water, or we will consider water in a moment. And then these ions are diffusing in this implicit solvent model for water. Also, another input parameter is this electron transfer rate. So that is related to the inverse of time that it takes for the electron to jump into the cation. And this is something that is a parameter in our model, but can be actually computed using more sophisticated methods like perturbation theory, or perhaps something based on Anderson-Newton's Hamiltonian. Okay, so then to make sure that you have a steady current in the system, then you need to enter new cations every time one of these cations is neutralized, okay? Otherwise, the charge will disappear. So in order to do that, so then in this way, we can ensure a steady state current, as I say. So then these effects, they need to be synchronized. So we need a time description for the problem. And then we can do it using a Monte Carlo scheme in which we treat the diffusion in a kinetic way. So this I will explain in a moment how it works. So then the output of this, of a simulation like this would be like the overall electron transfer determined by this electron transfer rate. Also, we would like to see what is the distribution, how is the distribution of cations close to the electrode. And also, since we are dealing with kinetics here, then also we can also get information about the diffusion constants of the ions in the system. So, okay, now I will discuss some technical aspects. Electrolyte model is very simple, so it's a proof of concept right now. So then we have the primitive, this primitive model that is simply based on having charged spheres, different charges, plus minus, 2 charges plus minus. They are hard spheres, so they have a distance of closest approach that defines our unit of length. And then this system is in contact with an electrode that is simply a charged surface that it doesn't have any structure here at the moment. This can be changed, of course, when we refine the model. And there is simply a uniform charge density associated to this electrode there. So this model is very idealized, but still very much discussed in the literature. The equilibrium state of this system has been characterized using Grand Canonical Monte Carlo. So this is done, and this is possible because of the implicit solvent approach, because of the low packing of the ions that you have there, and also because of a low Coulomb coupling that you have in the system. So then we consider a spherical electrode model that you can see in this way here, representing here the different spheres, the cation and anion. And now it makes sense why I was drawing this at the beginning of the presentation, this electrode with some curvature. So essentially, what you have is here is the ions identified with different colors. Here, the different colors simply means which ions are close to the electrode, so which ones are in the active region. So in reality, the electrochemical interfaces interact only with the bulk. So in principle, there is an interaction with the other interface, but we have plenty of electrolyte here. So then in principle, they interact with the bulk. And the current computational methods, they are not taking this into account. So this is a way to do it. So we only have an interaction with one surface. So then what we do is perform the grand canonical Monte Carlo steps here in this region that corresponds to 50% of the volume of the electrode. Of the half electrochemical cell. So then the advantage of a method like this is that, yes, so we have only one interface, and we decouple from any other interface that might give us some artifacts. But the disadvantage, of course, is that all quantities depend on this curvature. But we have verified that under certain conditions, this dependence is very small. Okay, so now we go to the kinetic interpretation of Monte Carlo. So then, as I say, we have a competition between this electron transfer and ionic diffusion. So then the diffusion of ions is a kinetically activated process. That means it depends on some energy barriers and temperature. But actually, we can relate the time, the Monte Carlo time. Every time you perform a Monte Carlo step, you have a time associated to it. You can relate this time with the real time of the system by looking at the diffusion of the system, at the self-diffusion constant of the system. So then essentially what we are looking at is a situation in which the behavior of the mean square displacement when we perform the Monte Carlo simulations that we are going to perform on this system, actually behaves in the linear regime. So in this linear regime, you can extrapolate the diffusion constant. And then also, we expect that the real system behaves in this way in the diffusive regime. So then there is a simple way to relate the delta tau, which is the Monte Carlo time, with the real time of the system. So you can also, in principle, take the diffusion from experiments here and perform the same exercise here. So now we have a diffusion as a clock that actually is giving me the evolution in real time of this simulation setup. Now, the position of a new charge within the system, this is important because, as I say, we need a steady current, right? And this, we do it simultaneously in this model. So what is happening here is that an electron jump neutralizes this cation. But then instead what we do is, once we identify one cation that is going to be neutralized, we just simply move it randomly inside the simulation box. In this way, we make sure, this is the most important part, or this is what our goal is, to make sure we have a steady current. Also, we make sure that the constant charge of the system remains constant, which is convenient for us. And this situation mimics, of course, planar electrodes. These moving charges around immediately introduces a violation of the continuity equation. And then, okay, so a way to mitigate this problem is to introduce ions at random positions within the simulation box with this probability distribution. So that means that we are violating this continuity equation everywhere a little bit. There are other alternatives, of course. So now the details of the algorithm, and then just to see how it works. So first we start with a grand canonical Monte Carlo of this configuration at a given concentration and temperature. So then the system is initialized at certain time. Then we identify the cations that are active. So that means that there are some distance, delta R, with respect to the cathode. And then sorry, you have a question?
Sorry to interrupt. So I might miss something. So after you reduce the cation, how do you balance the ions?
How do you
balance the ions? Do you remove an ion or you change the number of ions?
No. So then in the grand canonical setup, you introduce ionic pairs, so you keep the constant charge in the simulation. So you always keep here a charge sigma, right? And then you remove, so the electron jumps, so then let's imagine that this is actually connected to a reservoir of electrons, so it's at some voltage. And then you remove, and then you move the cation inside the simulation box, somewhere here within the simulation box. So we keep total charge constant in the system. So then we...
Sorry, also the question, the metal is removed. Sorry, the metal, I mean the neutral ion then.
No, the neutral ion, there are no neutral ions. We simply just move this ion here. And this corresponds to electron transfer.
So after the electron transfer process?
Yes. So this is, so once you, so let me get to this point. So then you identify those cations that are close. You give a random variable here, which is associated to each active cation in this case. So this is a first Pasha's time, right? Then when the simulation, then you keep moving the number of all the ions with Monte Carlo steps. And then you associate a time for that. Then what happens is that at some point you see like, okay, which active cations I have. Everyone has a time, associated time. There is a time for the simulation. And wherever this condition is fulfilled, then you have a change in oxidation state. When you have the change in oxidation state, I'm here representing this as a neutral ion, but there are no neutral ions no neutral particles in the simulation box. It's simply like, okay, you just remove the positive one here and place this somewhere here in the simulation box. Okay?
But why?
So this is equivalent to half.
You try to do thermodynamic equilibrium. In a kinetic way.
Yeah.
Right,
Yeah. No, it's fine. Thanks. So then we insert this cation with this probability distribution as given here. So then we update the list of active cations, and then we keep going with the simulation, right, until we reach some final time. Yes. So here's a few comments about the algorithm. So each electron transfer and cation repositioning is a process that takes place a priori. So there is no acceptance or rejection here. So once simply we have the correct time, then this process is bound to happen. And then we force the ion, in this case the cation, to go inside the simulation box. If they overlap, then we find a new position until we find a position that is suitable for the move. A priori, constant electron transfer rate constant. This is the same for all active ions. Doesn't depend on the distance from the ion of the interface. So this is one assumption that we have, and it's actually related to the type of simple metal structure that we are considering. If we want to modify this type of metal surface that we have, then we will need to change this condition over there. Also, this electron transfer rate is independent of the electrostatic potential, meaning that, so you have a reorganization of cations close to the electrode. For every cation, you will have an electric field that is produced by all the atoms that are around. And then, of course, this electron transfer rate should depend on this electric field. And this dependence we have not included. In this model, as it is now, we will see an example of what happens if we do. Indeed, modeling this, including this distance and electrostatic potential dependence on this electron transfer rate, is required to reproduce the Volmer-Butler condition. Okay, so let me see if this works. So this is a bit a summary of what is going on. So then you have this electronic structure close to the electrode, and this is what is happening. So there is a reduction here. There is no neutral particle, just a new ion is somewhere placed inside. Then we keep moving the simulation with Monte Carlo steps. Time keeps advancing, and then we update the list of active cations. Yes?
I'm still wondering why you do not, why these neutralized cations, why they don't stay there. Because the reality is forward and backward reaction.
They are not supposed to stay there. They will diffuse because they are no longer attracted to the electron.
But if you have a zero concentration of the species, actually, then you're under fully uncontrolled thermodynamic conditions.
No, we control the actual concentration of ions, and this is constant.
Yeah, for the forward reaction, but not for the backward reaction.
No, but then in any case, you have in this system, imagine it's infinity, so it's a real system. Yeah, so then you have a charge entering the system.
But infinity.
And the diffusion leaves. So then what remains in your experiment is a concentration, is a fixed concentration.
But infinity is not well defined in thermodynamics. I mean, this is at zero concentration. This is an infinite free energy
No,
change.
this is not zero concentration. There is a fixed concentration of ions, and this is the parameter of the model.
Talking about the backward reaction.
What do you mean by backward reaction?
Backward reaction this reaction is a forward reaction, right? Electron transfer to
I'm
metal.
considering only half self, which means that there is only one reaction happens here, the reduction one. This is the only one that I'm considering.
Why is there not the backward reaction? M reacts
because
to H.
I'm interested only in the half cell model. So I'm looking at reactions happening at one electron.
But at every interface, forward and backward reactions are happening. So M reacts to M plus and electron on the surface, always. Why wouldn't that happen?
Yeah, this is happening. So M reacts with the electron. So there is a neutralization. So that corresponds to placing the charge anywhere else. So this is the trick.
Okay, maybe that's correct that this is the backward reaction. Okay, maybe that's correct. Sorry. Yeah.
Okay, no problem. So then, okay, we go from a few details now. I will skip a few details now because they are not really crucial, but actually we can calibrate this time scale for diffusion. So then, of course, the conversion between real time and Monte Carlo time it depends on the amplitude of the Monte Carlo move. So this we can see here. We can indeed, perhaps more interesting, change the amplitude of the Monte Carlo move and fix the conversion rate between real and Monte Carlo time. In this case, we are talking about of the order of nanoseconds. And because the time step is precisely of the order of nanoseconds, this is why this method, we prefer to use this method to molecular dynamics, because we really go beyond this time scale limitation. So, okay, so one result here is we have a steady current through the half cell. So then here we compute the number of electrons that have been transferred to the electrolyte as a function of time. And then we see that this is growing with the charge of the surface. So the more negative the charge, the more intense this effect becomes. So this, so you can read here this. I will save some time not discussing the simulation details. We can just discuss them later if you want. So then this steady current forms after a short transient, which is last around of 20 nanoseconds. From the slope of this curve, we can get the current density as a function, in this case, of the surface charge of the electrode, and also in terms of concentration of ions. Then we see that it increases non-linearly and rapidly, not only with the surface charge, but also with the concentration. Here, I just want to point something interesting. Zero charge, yes, of course, you have a non-zero current in the system. So then this is just due to the electronic structure close to the electron. Yes, I mean, this is also some exploration. We explore the effect of the Monte Carlo amplitude step in getting the same value for the current density, and then we see that in this broad range, it doesn't change much, so we can get always the result. The only difference is the simulation time that we need to converge the simulation. But okay, so this should be, perhaps due to the fact that the system is relatively simple, and then we need for more realistic systems to tune this Monte Carlo step more carefully. Okay, so this is an interesting result because it shows how this model really goes away from a mean field description. So then here what we have is the density of the anions and cations as a function of the distance to the center to the center of the cavity. So here we have precisely the position at which the electrode is. So then if the electron transfer rate is 0, then we have a monotonous behavior, no, for the density, and clearly, well, it's not a surprise. So then the cations would like to get close to the electrode. There are essentially no anions close to the electrode. But then as soon as you increase the electron transfer rate, there is this anomaly that appears precisely at the boundary of the active layer. And this is due to the fact that you are really neutralizing cations faster than cations can come back and fill this place here. So this is this effect here. So then actually we can compute how this density, or the current density, depends on the associated current density, depends on the electron transfer rate. We will expect something linear, but instead we observe an actually non-linear behavior. So then when the electron transfer rate is small, then you see that, yes, there is this quasi-linear behavior here. But then as soon as you increase the electron transfer rate, you see this deviation from linearity. And this is due to this fact of this depletion of cations that is happening faster than ions can organize in the system. So then, of course, we expect much stronger violations on this mean field behavior when we consider the dependence on this electron transfer rate with the electrostatic potential and also with the distance, for example. So here we are just verifying that the density, so this is the condition that we want, that the current density is uniform across the radial direction, pointing to the center. So this is the center of the cavity, and here you have the position of the electrode for all the cases here. So then, as I said before, a violation of the continuity equation is unavoidable. This perhaps is something that happens in experiments as well, because you have a charge entering and leaving. So then perhaps this is something that we can use also to tune the model to reproduce more realistic conditions. So as I said before, the density functional, for example, cannot take into account this granularity of this process. Here, instead, we have a discrete description of ions and electrons. And then we can analyze the effect of noise in this current flowing through the sample. So in this case, in particular, we have just an example, probability distribution of the time epsilon separating two successive electron transfer events. And this as a function, or the plot in terms of the surface charge of the electrode. And then you see this behavior that is well reproduced by a Poisson distribution. Then we expect, again, to have more interesting, perhaps more counterintuitive effects when we have a more complex description of the electron transfer rate. We can also investigate the dependence on the current density with viscosity. And this is because, you have current density. Current density depends on diffusion, and diffusion is related to viscosity via naively the Stokes-Einstein relation. So then we can tune the model to reproduce different viscosities. So we are exploring here 4 orders of magnitude for different viscosities in the system. We see that at high viscosity, the electron flow through the system is limited by the diffusion. Instead, at a low viscosity, the transfer rate is what dominates the underlying overall electron transfer through the sample. So now we look at the relation. So first, this is, of course, we're interested in the current, but let's see first the number of active ions. So the density of active ions as a function, here again concentration, as a function of surface charge. So if you look at again, so this shows a violation of this mean field approximation in the sense that, you can write the density close to the interface, multiply this kBt times kBt, and then you will get a pressure. Then the pressure will be the pressure of the electrolyte plus the pressure induced by the electric field. This pressure is given by a Poynting vector, and the Poynting vector is proportional to sigma squared. So then you expect at negative large values of sigma, behavior that resembles a sigma square curve. But instead, the situation is a bit more complicated. We found that in this case, a description like this fits well different values of the surface energy, the different values of the surface energy that we have considered. And also, we also verified that this plot also reproduces the behavior of the current density as a function of charge of the electrode. Okay. So now I summarize. So then we have this, so this part of the talk at least. So then the Monte Carlo model for electron transfer and ionic conduction. So we have one synchronization of times. So in such a way that we can take both into consideration the time for the electron transfer and the time for the ionic conduction. Electron jumps from the electrode at a short range. And this rate depends using, again, Marcus theory, the reorganization of cations, the electronic structure, and so on. Then the electron transfer change the density of ions at contact, and this is partially balanced by the diffusion of ions that are far away from the electrode. Then we see also that our results show that the model this model reproduces this stationary state, so this steady current flowing through the system. So a bit of discussion on what to do next and how to improve. So again, this is a proof of concept, can be easily extended in many directions. One of the directions is precisely go to atomistic description of the cations and, well, the electrolyte and the electrode system. This is currently underway. Then again, the problem here, or the advantage and the reason why we use grand canonical Monte Carlo is because we have low packing, low Coulomb coupling, and implicit solvent model. But then we need for realistic system to have a proper or more robust grand canonical molecular dynamics or Monte Carlo simulations. So this is the idea is to use this adaptive resolution method. I will discuss this in a moment. This is really underway. I can show you very preliminary results of this. What is the effect of having the electron transfer rate dependent on the local electric field? And then, as I said, and I will show preliminary, this has the potential to reproduce the behavior expected from the Volmer-Butler equation. Also, and very interestingly, what you can have is a relation between the correlation of the cations close to the surface, right? Because they will organize, they will have a given electric field. This electric field will change the electron transfer rate, and then this will reorganize again the solvation structure close to the electrode. So this is also something interesting to explore. Image charges we can easily include. And then, of course, a better description of these quantum mechanical effects is something that we will like to consider as well. So now, as I said, this is very preliminary. We got the results last night, actually. So then electron transfer barrier on the radial electric field at the interface. So this is basically what is happening in the problem. So you have a barrier. So this is the electrode, this is the electrolyte, and the electron has to overcome this barrier. But then, since this is electrified, then the cations there generate an electric field that we assume is constant because this distance is relatively small. And then we see that the barrier is decreased by the electric field because the electric field is really pushing electrons from the electrode into the electrolyte. So then we have a net decrease in the free energy barrier that the electrons must overcome. This is again violation from mean field. So then we look at how the radial electric field behaves as a function of surface. Of course, you expect something that goes like proportional to surface using the standard electrostatics. But in this case, we have a distribution that is really showing that electrons, the form electric field is pushing electrons from the electrode to the electrolyte. And this lowers the free energy barrier, delta G. If we consider that this is a thermally activated process, then or thermally driven process, more precisely, then the dependence on this electron transfer rate, we can express it in terms of an exponential like this, proportional to the electric field. Now, if we compute the dependence on this of this quantity with the surface charge of the electrode, and this we can compute using the previous expression, and we compute this and plot it as a function of the surface energy of the electrode, then we see that there is an exponential dependence between these two quantities. And this reproduces the Bolmer-Butler equation, because actually we have this quantity here that is proportional to the current density, and this quantity here is proportional to the applied voltage. So this is a very nice result. Still being analyzed, because as I said, we got the results last night. Okay, now I have, 14 minutes, I guess. So then I will discuss these methods, how to perform molecular dynamics Monte Carlo simulations using open boundaries, actually simulations in the Grand Canonical Ensemble for realistic atomistic systems. This is not an easy task. Usually those methods are based on particle insertion. When you try to insert a molecule, a full molecule, in a very dense liquid or highly concentrated, then the steps are really unfeasible sometimes. So then we rely on this whole idea developed in the group of Kurt Kremer at the Max Planck for Polymer Research. So then essentially what we have is one simulation box. In this simulation box, we have the coexistence between atomistic and coarse-grained representations of the same physical system. So then what we want is that the molecules change resolution on the fly. So then when one molecule is here and moves into this part of the simulation box, it becomes like coarse-grained. And we also want that atomistic and coarse-grained descriptions are at thermal and chemical equilibrium with each other. Everything is modulated by this switching field lambda, takes values 1 in the atomistic region, 0 in the coarse-grained region, and something in between in the hybrid region. So the first realization of this model was based on the force interpolation. So that means particles here feel a bit of coarse-grained force and a bit of atomistic force. And there is another variant of this model in which you interpolate energies. This is the one that I will discuss because with this one you can write a Hamiltonian for the system. And if you want to do statistical mechanics, then it's better to have a Hamiltonian. Actually, one of the things that we realize is that this is nothing but a reference system for this atomistic system that we have here. So in principle, we can even have an ideal gas. So a very reduced model, very cheap computationally. So this is what you have here. So an atomistic and ideal gas representation. Ideal gas means simply non-interacting thermalized particles. We can write the Hamiltonian in this way. You can see now that when lambda is equal to 0, then you have only kinetic and intramolecular terms surviving. When lambda is equal to 1, you recover the fully atomistic Hamiltonian. We have an external potential here that at this point, we don't know what it is. But this Hamiltonian is actually equivalent to have a inhomogeneous fluid under an external field, and this admits a solution using classical density functional theory. Yes? This is periodic. Yes, thank you. This is fully periodic. Fully periodic. Thank you. So then, because of that, then you assume, at this point we are assuming, and this is important, we are assuming that this ideal gas is in the Grand Canonical Ensemble, that the whole system is in the Grand Canonical Ensemble, so we can write the grand potential, and then we use this functional form of the Legendre transform that relates this potential with the free energy of the system. We write it as a function of the density. So written in this way, just a cost function. So it tells me like, okay, what is the cost in free energy for the system to be at this particular density? As a cost, it can be minimized. And then if you minimize and you impose certain conditions on the system, like for example, you don't want any free energy barriers, and this is just for thermodynamic consistency, then you find a density profile that depends on this external potential and the excess chemical potential of the atomistic system with respect to the ideal gas. Okay, so here is the connection with density functional theory. We say, like, fine, I don't know what is this external potential, but I can check what is the density. I can manipulate the density. Actually, I can apply forces here to make the density the way I want, and I can integrate those forces, and I can get energy contributions that I can put here in this Hamiltonian, and this will give me the external potential. In particular, if I say, like, okay, I want the density of the system to be completely uniform, constant across the simulation box, then what you end up with is that this external potential is nothing but the excess chemical potential of the system. So this is immediately a nice way to compute chemical potentials of molecular systems, which are difficult to compute using other methods. So the example that we are most proud of till now, there will be something that will come later, and it will be even greater, is the excess chemical potential of aqueous sodium chloride. So this is how the simulation box looks like in this case. So we start with an atomistic simulation, and then we define these areas, atomistic, ideal gas, the hybrid region. In this hybrid region is where we compute the forces to make a flat density profile. Now we compare the excess chemical potential of sodium chloride as a function of concentration, water as a function of concentration. We compare with the most sophisticated results that we could find for this system using the bar method, which is a very, again, sophisticated way of using a particle insertion method. And then we see that our results reproduce reasonably well the behavior expected from the bar method. But also, when we increase the concentration, even though this is non-chemically sound, but this is just a model in this point, but when we increase the concentration of ions in the system, this is where this method starts to suffer. Actually, our method outperforms because we have more statistics in this hybrid region, and then we can predict the behavior upon increasing concentration or increasing density. Okay, so now we want to prove in the last few minutes that I have that actually this method is sampling the grand canonical ensemble, because we assume this from the equations that you saw, and we found a nice correspondence with the chemical potential, but we don't know if we are really sampling the grand canonical ensemble. So then we perform this exercise. This is part of Mauricio Sevilla's PhD thesis. So then the idea is like, okay, so let's consider these three simulation boxes. This is a fully atomistic simulation box here. And then what we are going to look is at the fluctuations of the number of particles with the different subdomains within this atomistic region. So then if you perform this exercise in a fully atomistic simulation box, a cubic simulation box, and then you reach the size of the simulation box, then the fluctuations of the number of particles is zero, right? Because there are no more particles to fluctuate. There is no reservoir. In this case, it won't go to zero because still you have this as a small reservoir. But it will tend to go to zero because it's, in any case, a finite system. Then we will see, okay, what happens when we have the adaptive resolution setup in which we have an atomistic and an ideal gas representation. Okay, and then let's see what will be the result. We expect that it will behave similarly to the fully atomistic system. Perhaps we can increase here easier the size of the system because it's just an ideal gas, but perhaps there is something more clever. And the something more clever is actually, well, this system is very reduced in complexity, so we can perform a grand canonical. Essentially, we could perform a grand canonical in this case, since it is an ideal gas, it's just particle insertion deletion steps. And this actually gives me this system in contact with an infinite reservoir of particles. Otherwise, I mean, in other words, a grand canonical simulation setup. And this is what we expect to see, and actually this is what we see. So here you have a comparison between canonical and grand canonical, fluctuations of the number of particles as a function of the volume of the subdomain in this atomistic region. When we get here to 1, that means that we reach the size of the atomistic region. Then for the fully atomistic system, you get this behavior here in red. So the curve is bending and it's actually going to 0. No? As soon as you reach the full size of the simulation box, then you will go to 0. Here you have the grand canonical behavior. This is what you expect. Actually, this quantity in the thermodynamic limit will give you the isothermal compressibility of the system. Okay? And then the adaptive resolution is somewhere in between. It's actually tending to the behavior described by the canonical ensemble. But instead, the adaptive resolution with particle insertion reproduces perfectly the behavior expected in the grand canonical ensemble. So in this way, we are showing that this adaptive resolution with particle insertion steps is actually sampling the grand canonical ensemble. We have more examples of for different systems. I mean, at the moment, we are playing with simple Lennard-Jones fluids. In this case, we have a mixture. We compute, in this case, Kerckhoff-Buff integrals. Kerckhoff-Buff integrals are also extremely size-dependent. We are computing here local excess coordination numbers. And then we see that this is the expected behavior analytical in blue, and those red points are the values obtained with the adaptive resolution. This, again, shows us that we are in the grand canonical ensemble, because if we are not in the grand canonical ensemble, we will get a value that tends to minus delta ij. This you can show for a closed system. Then, of course, we can look at phase transitions, coexistence curves. In this respect, Lennard-Jones is a very, very nice system to work with because it has all these features. So when you perform a simulation in the canonical ensemble and you approach these critical conditions, then you nucleate these two phases, the liquid and vapor phase, and then you create an interface there because the system wants to really coexist in the two conditions, in the liquid and vapor phases. In this case, we don't observe that. We actually observe that the system is fluctuating between liquid and the vapor, as expected. We can also, as a bonus point, compute the chemical potential of the system as a function of temperature. It's not an input variable that we have to add in the system, like with the grand canonical Monte Carlo, for example. Yes, here we show that there is a real coexistence between the vapor and liquid phases in these two plots here. So okay, so then you might ask, okay, so this is nice for a simple system. So what's going on with the original electrolyte? So here I can show that the situation works for in this case an ionic liquid. So there are few catches here. So we drop this ideal gas representation. Instead, we have charges. So we have a constant charge across the system. So then the reference system in this case is just a Lennard-Jones plus minus. Then in this plot here, what you see is how the density profile is evolving with the simulation time. And as this density profile becomes flatter, then we are converging this so-called excess chemical potential, but it's actually the difference in the free energy between these two representations here. So this is the current status of this model. This is something that we're investigating. Actually, for the first time, we will be computing the chemical potential of an ionic liquid, which I think is a very interesting result. This we will get from here. So with this, I'm done. Thank you very much for your attention and for all the questions along the way. So this is better because I can clarify a few things also for myself. I would like to thank the funding agencies and, of course, Kurt Kremer for insightful discussions. Thank you very much for your attention, and I look forward to your questions.